We're very happy to have Manuela Kulaxizi, who will tell us about phase shift and two-sided geometries. Manuela, the floor is yours.
Sorry. Hello. So let me start again by thanking the organizers for giving me the opportunity to speak and for ensuring that we have like this pleasant conference. And maybe I'll start with a disclaimer. Unfortunately, some of you might be disappointed. There is not, the results are kind of preliminary, so I didn't want to expose myself. So I will leave you mostly with questions regarding the topic rather than with answers at this point. So maybe the motivation is not necessary, but we all start with something like that, so let me do the same. So the topic of discussion for my talk today will be understanding or trying to understand some things about gravity and black holes using the holographic principle. And we will start modestly, so obviously we would be more interested in understanding gravity in flat space that we live in, but the holographic principle that we know very well of and have a very good handle of is valid for ADS space-time. So this will be the toolkit that we use, ADS space-time and therefore conformal field theories. So what we are going to focus on is basically a class of conformal field theories that will term holographic CFTs, and I will describe a little bit what I mean with that. It basically includes some minimal ingredients that we already have like a knowledge of that will give or that make us hope that the theory will have a holographic description. And so in this context, things that we would like to study are CFT correlation functions and on the other side in gravity, gravitational amplitudes. But this will be, the spirit of this talk is quite different from what we heard earlier today, for example, from the review talk, where you were looking at some specific example of holography. So in general, in this game, what we use are obviously consistency conditions, and these would be like unitarity, causality, the periodicity condition when we look at thermal CFTs. And also for CFTs, we have the consistency conditions of crossing equations and the OPE. And I just wrote here schematically a 4-point function of two pairs of identical correlators, which mostly will be the subject of my talk, and what I will call direct and cross-channel, loosely speaking, for this talk. So in the direct channel, we are taking the OP of the same operators, and in the cross channel of the ones that are not the same. So what I have in mind with holographic CFTs are CFTs that have the following ingredients. One and most important of them is that they contain an energy momentum tensor, and another one is that there are certain large parameters, in fact, two large parameters, around which we will expand our correlation functions. And one of them is the central charge, or the coefficient rather, in the 2-point function of the energy momentum tensor, that loosely you can say also characterizes the number of degrees of freedom of the theory. So we will be working in the limit where this is very large, and to have like a contact with ADS5 cross S5 and n equals 4 superior Mills in 4 dimensions. The CT is like n squared. So we're basically going to look at correlation functions in this, expanding in this parameter. And we know that the first leading term, the correlation functions factorize. The other characteristic scale is the gap. So what we call delta gap here. So this is we will assume that the conformal field theory that we want to study contains only a finite number of some primary operators. I call them here single trace. This is probably a not very good nomenclature in this context, but that's what we commonly use. And we have it borrowed from gauge theories. And we will assume that it contains only a finite number with spin smaller than or equal to 2. In fact, this has been shown to be a necessary condition for the theory to have, like, to leading order and Einstein gravitational dual description. And in practice, in this context in which we will discuss, we will be focusing perhaps on taking some, considering more terms in the 1 over CT expansion, but we will always be thinking of the gap being infinite. So in this game, we have like this basic, so to speak, ingredients that I refer to are what we would call the single trace primaries. So this is like a finite number of operators, perhaps scalars, other conserved U1 charges, and the stress tensor. And then from those, we can make what we call double and multi-trace primaries in general gauge theories. And here I schematically describe them by including derivatives and having contractions between them. And I also present, like, roughly the basic rules that we know for the theories that we have examples of how things, let's say, work in a perturbative expansion in 1 over CT for us. So in this general context, there's been a lot of work, and people have used the crossing equation and have, in some ways or other, proven locality or used unitarity in the crossing equation, and they have proved important theorems such as that you cannot have higher spin than 2, or like that you have indeed Einstein gravity as your leading order description. And or they have computed correlation functions, and actually with these minimal ingredients, you could even do that in certain kinematic regimes. And they have obtained order by order the CFT data that would be that make it responsible to reconstruct, in a sense, the gravitational background. That is basically OPE coefficients and possible anomalous dimensions that some of these building block operators acquire. And there has been even more recently, with the eye to window into the black hole physics, of course, a discussion of what is the thermal CFT structure, what are the quasi-normal modes, and things like that, and many, many, many more results. So I'm actually really sorry about this list of authors. To be honest, I had a list of 50 more plus people, but then I got really worried that I might have missed somebody. And then if you have 50 people and you miss somebody, then it would be really bad. So I opted for that, but I apologize for those of you whose names are not, and they should have been on the slide. So the focus here will be on something that we will call a sector that shows up in many correlation functions, and that we term the multi-stress tensor sector. And this contains a class of operators that are present in these generic holographic CFTs made out of the basic building block of the energy momentum tensor. So I schematically have them here. You see that I don't have explicit boxes in between. That's not because I'm considering different structures, but I just want to mean, that here we are implicitly implying all, in each of the series, we have these and all the possible contractions that we can make. And here I just denote the minimal twist of each of these series of operators that you find. So these multi-stress tensors play an important role, particularly in a specific class of correlation functions that we call heavy, heavy, light, light correlators. And these are 4-point correlation functions where two of the operators have conformal dimension that scales with a central charge, and we will often want to focus on keeping, as Ct goes to infinity, the conformal dimension of that operator to scale similarly with Ct, and therefore being fixed, this ratio. And the light operator is any operator with some with the conformal dimension that is of order 1. So this is, of course, very generic, and here, the way we play this game, we do not specify what this heavy operator is, and that is really perhaps a caveat of the fact that we are not looking at a specific theory, but on the other hand, we'll see that we can get a lot of information out of that. And then we can go to specific examples, like most of them are integrable, but still, and study what are the properties of these perhaps heavy operators, like we heard in some talks, and we might hear in some more ones. So this will be the main object of the discussion here, and this is also interesting because this operator, heavy, can be thermal, so the correlation function that we will be looking at could be a thermal 2-point function of these light operators. And we know that by the ADS50 dictionary, that would correspond to a 2-point function that you would compute by studying fluctuations in our ADS black hole background geometry. And so this correlation function is interesting because it will contain data that will allow us perhaps to understand something about black hole physics. So in terms of the parameters that we have abstractly defined in the context of the CFTs, we will be working with this parameter mu that, for example, in d equals 4 is related to the ratio of the horizon radius to the ADS scale. And this is precisely what we ideally would like to keep fixed in our discussion of the correlation function, which is the ratio of the scaling dimension of the conformal dimension of the heavy operator with respect to the central charge. Now, there is a bonus in studying these correlators, and this bonus is that we are getting, when we are considering fixed mu, we are getting, or if we look at an expansion rather, order by order in mu, we see that we get some diagrams enhanced by powers of this, by the fact that we have this delta heavy over Ct, while others that would be of the same order, loop order, in ordinary amplitude scattering expansion, will not be present here because they will not come with the same powers of delta heavy over Ct. And here, for example, you immediately see that the self-energy diagram is not there. So here I have really shown here the double lines correspond to the heavy operator and the one line to the light operator, and these are like Whedon diagrams in ADS, and the exchange is mainly of gravitons, and these will roughly correspond to the stress tensor sector and these multi-stress tensors that we want to focus on. Obviously, you probably know that in practice, this is not the only thing, but there are also double traces that accompany this multi-stress tensors in all of these diagrams. So since we discussed, given the title of this talk, we are going to consider what we call the bulk phase shift. And this is something that we mainly define in what is a specific kinematic limit, which is the Regge limit or the aconal limit in the scattering amplitude business. Here, in the context of the CFT, we will have to put the CFT on the sphere. And this here is a description of basically of the heavy, heavy light correlator of, and more or less, how we set up our correlation function. Here in the bottom and up, we assume that we have these heavy operators that create the states. Now here, delta t equal to pi is the distance, the difference in the correlation when in time in pure ADS, but there is like a little shift. This is like x naught and phi, delta t, let's say, and phi, for the two operators where we place them. And this should be, this effectively tells us that they will be very close to being on a light-like distance, one with the other. So the object of the correlation function, I have schematically, unfortunately, written it here, contains a special integral over what is called the impact parameter space, which is, let's say, roughly a Fourier transform in one direction. And the point is that in this aconal limit, this object in the CFT is given in a very simple form as an exponential of a given phase in momentum space, which is probably known from the scattering amplitude literature. So what does this, we call it a bulk phase shift because of the way that it's defined in CFT language. But indeed, it has, in terms of gravitational scattering amplitude, it's more or less the natural aconal phase that you have seen before. So what is that? So you know that if this is something, some exponentiation that characterizes a number of diagrams, and this exponentiation happens when we take a specific limit. Unfortunately, here my conventions are opposite to what you heard in the morning talk. So this is a large S and finite t for the Regge limit. The S and t was reversed. And we consider a 2 to 2 scattering amplitude in flat space. So then you know that this exponentiation happens. And in practice, this result contains an infinite number of diagrams that basically exponentiate this graviton exchange diagram. So now you see where we are effectively going. This has been first defined in the CFT language for the four light operators correlation function. So if you wanted to study this object in the CFT, the dual gravitational description would be given by the amplitude in the aconal phase. So you would have to study a 2 to 2 particle scattering when the particles in EDS are very energetic, or equivalently, an equivalent description that you know is also valid in flat space is studying the time delay that it's induced in a particle, in a proparticle that crosses a shockwave geometry. So these have been studied and have been actually checked that, for example, this specific, which I presented somewhat schematically, is that in reality it was a little bit contrived, let's say, to understand why this specific correlation function would give you the analog of the aconal phase, is actually true, and was able from that to recover the standard answer that you have for the phase shift for this problem. So in our particular case, we would like to study that including the heavy correlator. So that's why we only have one integral here, because this is basically like does the role of a state for us. And what we want to, what that will correspond to is the case where one of the two particles is much, much heavier than the other. And why do we have that in mind? Because obviously this takes us to a particle scattered off the black hole in a Schwarzschild geometry. So in holographic CFTs, if you want to look at this particular kinematical regime, and you want to look at what are the operators that are exchanged in the direct channel, you can classify them order by order in this parameter mu, although actually to get some interesting result, you would like to solve this problem to all orders in mu. But let's start modestly, and you will have an infinite tower of operators corresponding to each order. That will be always a stress tensor, and of course a lot of double traces of the same spin that accompany that operator when it's exchanged. And so in principle, there is a whole machinery that would allow you to compute this order by order in mu, although in practice, most of the results are for leading order in mu. So what does this Fourier transform to the impact parameter space does for us is that in practice in holographic CFTs, it eliminates the contribution from the double trace operators. So then it mimics, in a sense, what we would think of in gravity, that we have stress tensor, then double stress tensor contribution, triple stress tensor, and so on and so forth. So this is why this is perhaps an interesting correlation function, an interesting kinematic regime to focus, and because we will in some sense, isolate that contribution. Now, the leading order phase shift you could compute with like very complex techniques that involve a Mellin space integration and this Regge limit and Regge theory. But after this whole song and dance, you can get a very simple result, the first order in mu, that you can see that depends on s, the square root of minus p squared, that has to do with it. Obviously, conventions that we have is basically our Mandelstam variable s, and this pi is the hyperbolic, the propagator in d-1 space, which is the transverse space to the space where the scattering happens. And you could see it even in the simple ADS cylinder in the previous picture. So this result nicely matches the ADS iconal phase because it's exactly the leading order result, and this is what you would hope for. Now, let's turn a little bit to the black hole case and try to do the same computation. In that case, you will define there is, of course, a way to consider the computation in terms of scattering amplitudes, but here we will just try to sidetrack this, and because we're not interested in any massive particles, but in a light particle in the context of a heavy one. And so we are going to look at the time delay and phase deflection that a particle, that a null particle, because it's very highly energetic, that travels in the ADS-Schwarzschild background, admits it. So these are the two quantities that we have to compute, and we can define, in a sense, the phase shift in terms of these two quantities. We have the symmetry to set other parameters to 0, and you see a specific, other coordinates I meant to 0, sorry, and you see a specific parameter showing up, which is what will encode the impact parameter, which is necessary in the definition of the phase shift. Okay, so I'll try to speed up. So null geodescics are labeled by this impact parameter, and for mu equals 0, this reduces to the standard definition for the impact parameter. For large ADS radius or small alpha, this leads, sorry for the mistake, to the flat space expression. So you can get results for flat space from this computation. If you add all the ingredients, you get a nice concise formula for the phase shift, and this is the turning point within the bulk that the null geodesic approaches before it returns to the boundary. And this is this 2. So to match with some CFT result, you remember we showed an impact parameter parameterized by L. You can relate it in this way. That's just to know that in principle, there are just two parameters in the phase shift, S and B. S, the Mandelstam variable, and the impact parameter. So the integrals are not very complicated, and one way to do it is directly. You have to use some complicated hypergeometric like Loricella functions with many variables, but that's doable. Another way to do it is to do order by order in mu expansion, and then you'll notice that a nice concise expression comes to each order. In fact, the contribution to the phase shift has exactly the same form. Mod is S here, and that is something that you would expect. We're working in gravity, so you want the scattering amplitude to go like S to J minus 1, and J has to be 2. So all of these terms should give you the same effective contribution. And then this pi is again a hyperbolic propagator of the transverse hyperbolic space, but now it is as if it is a higher dimensional space. In fact, it corresponds to a maybe region spin 2 particle that would be conserved, and that would be the result of the summation of this infinite tower of multi-trace stress tensor operators, and would have the same twist, the minimal twist of that tower. In any case, the minimal twist corresponds to a conserved current, okay? So the reason we see some mild conservation here is that to this order we're playing the game, these multi-stress tensors do not, their conformal dimensions do not get corrected. So, but we see something else, and this is that you could see even in the normal amplitude description, that there is like a radius of convergence for this series, and this is when this impact parameter gets a critical value that corresponds to the particle not returning to the boundary. It starts orbiting, this is the photon sphere first, and then we lose it from sight. So what we're going to discuss here is what we can do in that context. So for values beyond that, the particle falls into the black hole. In some sense, this is inelastic scattering. So the phase shift acquires an imaginary part. You can compute it. There is an absorption cross-section that you can compute. And that was actually done. And the result was shown to reproduce the correct geometric absorption cross-section. Yeah, that's good. I had another slide, so there's no time. So in the computation here was done in the asymptotically flat space limit, which you can take for when the radius of a disk is large. But then the point is that the results would be the same anyway. But the question is, why do that? You could do something else. What could you do? You could say that since now my particle doesn't come to the boundary, I forget what I have computed, at least in gravity, which was based on the fact that there was a turning point, and I'm redoing the computation from for the particle going all the way to the singularity. So if I redo this computation, what do I expect to get? Perhaps a different imaginary part. The point is that there has been a lot of discussion about that, and there was in earlier work. And one could see, for example, if just computing the time delay, if you fix the angular variable to be the same, that if you do this computation, you get the particle is in some sense that you lose sight from it on one side of the black hole, and it appears on the other side. Thanks to these authors, this was shown if you consider the two-point function of operators in the thermofield double state. And now, however, these light operators that we were considering before have to be thought of as living in different boundaries, will be correspond to a correlation function of operators of the same CFT with a shift in time that will depend on beta over 2, where beta is the inverse temperature. So you can actually try to do this computation. You can include angular momentum in gravity, and you can do this computation, and you can see that the imaginary part of the phase shift is proportional to the temperature, and PT is the energy, the total energy of the system. So the question now that happens, I'm sorry, I'll maybe need 2-3 more minutes. The question is now, are both continuations meaningful? And one can perhaps look at d equals 2. In the interest of time, I will not go through. Unfortunately, in d equals 2, where we have a handle on the full result, the situation is somewhat different because there is no critical impact parameter. When you are in the BTZ, the particle just falls in the singularity. When you are in a conical deficit, the particle returns to the boundary, and then you can confirm that the results work through. There is related work that has to do with particularly this two-sided business that you've heard, maybe it talks earlier by Cheplak. where one can compute this correlation function, where depending only on time, and sees that there is some critical time where there is a singularity, and this behavior is captured by the stress tensor sector of the correlator. So what I would like to advocate here is that perhaps this bulk phase shift, this impact parameter integration of this correlation function will be the right playground where to investigate the behavior of the stress tensor sector in these games, and also perhaps help us understand or redefine our understanding of inelastic scattering with what I said. So thank you very much.
Thank you, Manuela.
I'm sorry for the time.
No, we are a little bit short on time, but while the next speaker comes to the audience, there's time for one or maybe two very brief questions. Any question? I have a very quick one. How does it relate to if you take a sort of the standard geodesic action for a single particle approach to your results? Is there a limit where you recover that? Simply the...
You mean the length of the geodesic?
Length of the geodesic.
That is true for the space-like configuration. You can do that, and for our configuration, you can also look at order by order in that, and you can also recover it. Yes. Yeah. But I didn't look at it in the specific example that you're referring to.
Okay. Thank you very much.
What I mean is in the two-sided.
Yeah. Let's thank Manuela once again.
Thank you.